Believe it or not, I did something stupid. This thing I use, this panopto that I use for recording, has a little tick mark where you have to say whether you want to record the screen so that you can see the PPT or not. And for some reason, it got turned off, and so I recorded 35 minutes of podcast, but just my face, no PPT. So I have to redo this again. Anyway, it's a nice paper, so I don't mind redoing it again. This is from a large team from across the world, which is reporting on recent applications and potential of near-term, so interannual to decadal climate climate predictions. We'll see what it means. Quickly to read off, this is going to be a bit long, so pace yourself. Following efforts from leading centers for climate forecasting, sustained routine operational near-term climate predictions, NTCP, near-term climate predictions, are now produced that bridge the gap between seasonal forecasts and climate change projections, offering the prospect of seamless climate services. So basically, the climate projections focus on multiple decades out to 2100 and even beyond, and there has always been a debate about the uncertainties, scenarios, and whether they are useful and so on. And there is also some debate about whether we should have gone from weather predictions seasonal to interannual into decadal predictions, which can help policies, strategies, and so on, instead of jumping to 2100, because the projections are, they take tremendous amount of resources, people, financial and computational, and so on. So some case studies are presented here from finance, economics, water management, agriculture, and fisheries, which we will quickly look at. There are some technical details on how they are done, which I'm going to skip because I want to just give you a brief introduction to the range of things and some examples of the skill, so that you can then see whether you want to get into the details of how it is done. As an introduction, in climate prediction, the initial state of the climate system, including elements of the atmosphere, ocean, land, sea ice, and biogeochemistry, is constrained to closely represent a particular date via the introduction of observation-based data in the model initial conditions. In common with weather or seasonal prediction, starting from observed conditions is a prerequisite for predicting their subsequent temporal and spatial evolution. So predictions are initialized, whereas projections are initialized with just the CO2 level, and then you integrate forward. So the projection models are not trying to predict El Nino or decadal signals and so on. They are just trying to project impacts of increasing CO2 and so on the warming and the impacts on everything else. And they have many other things you have to worry about. As you go into the future, they need scenarios, which we have discussed elsewhere, and so on and so forth. Okay, so things that matter like aerosols, greenhouse gases, are also prescribed for the decadal prediction, because that's far enough into the future that fast changing things have to be prescribed, whereas in weather and climate predictions, obviously we don't often worry about CO2 changes and aerosol changes and so on. So we'll leave it there. The first example, finance and economics, current applications of and challenges for assessing climate-related financial risk. In recent years, the finance sector has made progress in understanding the different representative concentration pathways, which I have discussed elsewhere, and shared socioeconomic pathways used in Intergovernmental Panel on Climate Change reports. The range of different pathways allow for the consideration of a variety of warmer futures, each with different outcomes and impacts. Financial and macroeconomic modelers have sought to link these broad scenarios to financial and economic factors. I have podcasts on these elsewhere on translating RCPs and SSPs to financial risks from reports from the Federal Reserve and the Network for Greening the Financial System and so on. This linkage comes from the estimates of the overall levels of damage associated with each scenario and the resultant impact. The magnitude of physical hazards and their evolution over time can inform asset level estimates of risk under a given scenario. Damage functions are a way to provide a probabilistic view of potential harms an asset may face from a physical hazard. So it's a kind of empirical relation that takes aggregation of multiple hazards and the relation with, let's say, agriculture, infrastructure, housing market, whatever, and converts the physical climate change parameters, acute and chronic stressors, into financial risks. So this is how it works. Climate hazard is estimated, physical impacts on the entity are estimated, financial impacts for the entity are estimated, and financial impact for financial institutions like banks, which make, provide loans, invest in new housing constructions, new infrastructure. So they have to report their climate exposure as well. Okay. The second example is about decadal hurricane predictions for insurance. Insurance companies are always worried about how much they have to pay out in case there are hazards like hurricanes. Milton and Helen have destroyed large part of the eastern seaboard, southeast part recently, and billions and billions of dollars in damages will be handed out. Hurricane damage in the United States is rising as population and property in coastal regions increase, with Atlantic hurricanes now accounting for most of the insured losses in the US. Hurricane activity also varies on decadal timescales, with hurricane damage in the US varying by up to a factor of 5 between recent decades. Skillful decadal predictions of hurricane activity offer the reinsurance sector an opportunity to better manage these varying risks. So reinsurance industry, in case you don't know, is something that insures the insurance companies themselves. So they are really eager to see what the insurers are underwriting in terms of risk. Factors controlling hurricane formation include sea surface temperature, temperatures in the upper atmosphere, atmospheric stability, and vertical wind shear in the upper atmosphere. So your predictions have to track these parameters and potential for cyclone genesis and higher intensity cyclones, etc. So prediction models themselves do not explicitly resolve hurricanes, but you use these parameters to estimate hurricane activity in the future. On decadal timescales, these factors are influenced by the North Atlantic SST, which is highly predictable. So predictability is always important. Can you do better than just saying climatology will happen again? You must be able to say beyond climatology what is going to happen. That's prediction skill. Enabling skillful long-range predictions of hurricane frequency comes from this highly predictable North Atlantic SST. And here is a quick example of hurricane activity, accumulated cyclone energy in 10 to the 4 knot squared, obviously wind speed dependent number, which corresponds to damage. So central year of 5-year period going from 1960 to 2022 or so when the paper was published, and you can see the range, but the models do ensembles and so on, and you can see that the ensemble mean tracks the observed fairly well, and if it can translate to enough reliable information for planning, this is called a hindcast. So you go back in time, make the forecasts, and see how you do against observations to get confidence in the model's ability to capture decadal variability. Here is decadal predictions for commodity price forecasting. This is in triennial time scale. The El Nino Southern Oscillation has significant impacts on agriculture, water, and health, which we know well. Some of the nations that experience profound ENSO impacts are geographically small, located in or near the tropics, and have economies dependent on a few climate-sensitive industries. It could be just exporting wheat and rice like Pakistan does, or many African countries, Mozambique, corn production, and so on and so forth. They have economies dependent on a few climate-sensitive industries. In addition, there are documented relationships between ENSO and movements in commodity prices, agricultural production, and broader macroeconomic indicators. In that regard, this paper by Kitsiosis et al. Have demonstrated that econometric forecasts of certain commodity spot prices can be further improved with inclusions of climate predictions of the relevant indices of climate variability, i.e. exogenous factors. Here the highlighted commodity is coconut oil, and the exogenous factor is the Nino 4 index, which is an El Nino index from the tropical Pacific that you can look up elsewhere on my channel. The Nino 4 is chosen as coconut oil that is predominantly produced in the tropics where the physical influence of ENSO is most direct. So if you have no ENSO, then the forecast skill drops off. So ENSO has definitely an impact on the correlation coefficient at interannual timescales on commodity price predictions, and you want the correlation to be high enough at long enough lead times. You can see that when models do the forecast, the skill drops off at some point. Perfect ENSO basically means that the model is trying to reproduce its own ENSO, and there are some technical details. Nonetheless, it's an example of how commodity price index can be predicted based on the predictability we have in El Nino. But there are other issues. Who will use this information? Stock market people may misuse it, or drive prices up by betting in this way or that way, and governments can make decisions based on forecasts which can affect prices elsewhere. If India decides to reduce or stop exporting rice and wheat based on ENSO prediction, then prices in Indonesia for grains may go up because Indonesia may be importing from India, and so on and so forth. And that can happen even before El Nino comes. Okay, so water management and glacier loss, decadal prediction in the Wupper River catchment in Germany. The Wupper, I don't know how it's pronounced, by the way. The Wupper catchment water board manages water level and quality of the Wupper River in Germany. To improve water management strategies, multi-year predictions of the standardized precipitation index (SPI) are required, as this is correlated to dam water levels in the catchment. Multi-year annual and hydrological seasonal means are needed at high spatial resolutions to manage 14 dams in an area of 800 square kilometers. So you get skill level requirements from user specific sectors. What insurance industry can use is not necessarily what water manager can use in terms of the skill level, and lead times, how many months ahead you need this information, and at what spatial resolution you need this information. These are all sector specific information demands. Statistical downscaling from 200 km to 11 km was applied to all ensemble members of the decadal prediction system MPI SMLR, which is a German system. So here the global model for computational efficiency is run at a course's resolution, let's say 200 kilometers or even 100 kilometers, but you are requiring information at much higher resolution for managing these dams, which means you have to downscale them. So instead of just using the grid point information, using data and forecasts from the past, you can actually add value to downscaling and producing more reliable information locally. Okay. Relationships between large-scale temperature, relative humidity and geopotential height in Central Europe to local scale temperature and precipitation in Germany have been considered using MSEP analysis and high-resolution, high-res observational data. A lot of technical information, but don't worry about it. Geopotential height is something that is easy to predict and track, and is an indicator of local weather, and reanalysis is a blending of past data with models to produce dynamically interpolated historical information for calibrating, downscaling and so on, and high resolution observation data locally can add value in AI/ML as well for downscaling. Downscale precipitation has been recalibrated by applying decadal climate forecast recalibration strategy to correct bias, drift and conditional bias and adjust the ensemble spread. Ensembles are where you make multiple models simulations for forecast, because Mother Nature takes one track, but you don't know which track that will be, so you have to guess how many tracks are possible and then cover the range that Mother Nature is likely to take. Models have bias and they have a drift over time, and they have conditional bias and so on, which are corrected in various ways, and ensemble spreads are adjusted to account for those, etc., to make the information more reliable. The feedback of the Wupper Catchment Water Board concluded that the product is understandable and well structured and of utility during the daily decision making work of water boards in Germany. A high probability of drought conditions is currently forecast for 2021-2023, which you can go back and see if it came true. I'm recording this in October 2024. I didn't look up because I'm just trying to focus on providing this information. If I say, oh, it failed, then you're going to be distracted. Decadal prediction of for glacier mass balance. Glaciers are important indicators of climate change, of course. They also store 75% of the Earth's available fresh water, also acting as buffers preventing precipitation from immediately turning into runoff. They are essential parts of mountain water storage and supply downstream communities and ecosystems upon which 22% of the global population depends. Quantifying changes in mass balance is challenging considering glacier response times. In temperate maritime climates, this is generally between 15 and 60 years, but can exceed a century for high latitudes. It depends on snowfall rates and so on, and the warming rates. Decadal timescales are rarely considered in glacier modeling, even though they are critical for water resource management. By predicting glacier mass balance on decadal timescales, it's possible to predict runoff, an important input for water resource decisions. So that's the relation between mass balance and usable information or application. So here is an example, data versus model predictions. You can see it's done for 1982 through 1990. These are showing temperatures and not anomalies, so you can see seasonal cycle is well captured, but you can see that there are years where anomalies are not well captured, so you have to go back and see whether there is skill in anomalies as well. And predicting precipitation is always much harder than predicting temperatures, which I have discussed elsewhere. Temperatures have a nice large scale, and models are good at doing this, but converting that to precipitation is very tricky. Even in observations, we get contradicting information from multiple sources, so you have to be careful. But if you look at specific mass balance in millimeters of water equivalent, which is the way we do it, there are the ensemble members and there is the ensemble mean and the observed. So there is definitely some skill, and this is for cumulative mass balance in millimeters water equivalent. So again, over the same period, so year to year versus cumulative, you can see there is a decrease obviously, and the model is not doing so bad. Correlation coefficient is fairly high, so useful information is possible. Agricultural policy. Recent studies have explored the ability of decadal climate forecast systems at predicting extreme climate events relevant to agriculture, such as drought and heat stress conditions, on a multi-annual time scale. It's also called societally relevant time scale by some community members. Evaluating the quality of such predictions is considered a fundamental step because it assesses whether the prediction system can be trusted to reliably forecast multi-annual climate events. The results presented in this section reveal significant skill for predicting climate events for temperature and, to a lesser extent, for precipitation that are already being usefully utilized to aid decision making in the wheat sector, with potential further applications to viticulture, which is growing grapes for wine. Very powerful commercial business where they can put a lot of money to manage their losses or minimize the impacts and so on. So here are the forecast years 2015 to 2019. So hindcasts forecasted standard precipitation evapotranspiration index, which is about how much the yield will be. Starting date November 2014. So you can see below normal, normal and above normal regions are shown, and this is the observed index for the same period. The model has, very wrong here, but not so bad here, not so much skill here, and so on and so forth. So they have shown some gray areas with insignificant skill, white areas where there is no skill, and so on and so forth. And there are many issues. If there is skill here but not here, what does it mean? Obviously, this is an engineering approach where you can say if the model can reliably predict in one place despite deficiencies in other place, then we just use it for decision making. But in the background, the modelers will be trying to understand why that's happening and improve the model and forecasts and see if the right answer is being produced for the wrong reason. The metaphor could be that you have a car which runs but it pulls to one side, so you drive it carefully, but you have to take it to a mechanic to get it fixed so that it doesn't become worse and worse. Okay. Fisheries management, applications and opportunities for decadal forecasts in marine fisheries, aquaculture and conservation. Alistair Hobday is a big guy in this. For more than a decade, physical information about the future ocean has been used to produce ecological forecasts at both short and multi-decadal timescales. So here is Alistair Hobday from Tasmania, which does tremendous amount of work. Ecological forecasts exploit relationships between physical variables and biological responses to predict ecologically relevant information. I think Patrick Leody is also involved in these in this paper, and the references provided here. Another colleague and friend who works on modeling fish and tortoises and turtles and so on and so forth. Okay, this includes species. The predictions include species spatial distribution, abundance and phenology, seasonal migrations, etc. In recent years, ecological forecasts at seasonal timescales have also been developed for fisheries, aquaculture and conservation, corals, etc. Decision makers such as fishermen, farmers, managers and policymakers in these sectors are now including forecast information in their planning. These plans can be based on forecasts about a species spatial distribution, where the decision might be where to fish or farm, abundance and production of juveniles, where the decision might be how much to catch and or grow. So juveniles get, become adults, and something called recruitment happens, where some die, some are eaten and so on. But if you fish the juveniles, then you are obviously going to reduce the adult population and reproduction as well. So it's very critical. Phenology, such as timing of migration, where decision might be when to open or close fishing grounds. Growth and condition, where the decision might be related to stock productivity. While in theory decision making can benefit from prior knowledge of all these factors, in practice, most forecast systems to date have only focused on species spatial distribution. Okay, so here's an example of the skill, and you can see the correlations. Some regions have very high correlations, and some regions have insignificant correlations. But regions of interest include mackerel in solid lines, bluefin tuna in this dashed box, and blue whiting in this dashed box. So it's good news, right? This is for sea surface temperature and this is for salinity. The habitats for these fish depend on sea surface temperature, salinity, often dissolved oxygen and availability of prey, their food, forage fish and so on and so forth. So depending on how complicated the prediction system is, various factors are considered, but focus is often on making sure you can predict, or there is predictability in the driving physical conditions first, and then you can translate it into fisheries. And there are other ideas of extraction of weak links by ecosystems, where there may be small correlations between, let's say, El Nino and SST and salinity, but when you look at fisheries, they are combining both and producing a higher correlation with El Nino. So that's an interesting approach to look at. Here is an example of mackerel habitat in thousands of square kilometers, and two periods are considered. 1990, you can see the ensemble mean is not bad, ensemble spread is large, but it covers the observations. And this period from 2010 to 2019, the skill is not so great, because maybe there are several El Ninos here, 2012, 14, 15, strong El Nino and so on. So maybe the decadal forecast didn't capture the El Nino impacts, because remember, it's not an El Nino forecast model. So these things matter, and we have to learn to do that better. This is just an example of prediction of Labrador current temperatures in support of fisheries management. So Labrador is up here, and there is skill there. Obviously, you want to exploit that for managing fisheries. So this is looking at fractional area anomaly, forecasted versus reanalysis, or as4, and another one is analysis. There is a difference between analysis and reanalysis. Reanalysis is past data, past model simulations combined to give you interpolated climate reconstructed data. Analysis is where you take forecasts and provide the past observation, past information. Okay, so again there is skill and varies year to year as well, and there are some more details of forecast analysis, persistence analysis, and forecast of ORAS4. So you can take reanalysis as data and try to forecast that. So some nice details there, but you can see how anomaly correlations has various levels of skill, and there is always a threshold above which it is considered useful. And so these results indicate the potential utility of decadal forecasts for predicting subsurface ocean conditions relevant to the management of the northern cod population out to at least 1 year ahead and possibly longer, although further studies are needed to understand the differences between skill measures based on ORAS4 and CAN CM4 analysis. So what you are trying to reproduce may be different, so your skill may be higher with respect to one product and not so high with respect to another product. So then you have to understand what is the difference between these products. People use reanalysis products as reality without worrying about the uncertainties, but that's the nature of our business. So let's read off some future requirements discussion and summary. I'm being very brief here. These discussions are long in the paper and very nice. You should read if you are interested. Realizing the full potential of the near-term climate predictions in the marine sector will require overcoming numerous barriers within and external to the field of climate prediction. The most important of these is a need to raise awareness in the in the user and marine science communities about the current and constantly improving skill of climate predictions as is being done for seasonal forecasts. So people have argued that we had good skill in weather forecast, which is big business. People use it very well. Then you have seasonal forecasts like El Nino, which works very well. And then we jump to projections 2100 and beyond. So people didn't get a sense of what is in between. So decadal predictions offer a nice way to bridge this gap, meet the policy strategy decision demands at this time scale, and then maybe other purposes like resilience can be met with projections, because uncertainties are something to worry about. Considerable investment is still needed to support decadal forecasting and integration of those forecasts into decision support tools, especially considering the amount of resources we are putting into the projections. Overall collaboration between forecast developers and the marine resource sector is needed to support forecast-based tactical and strategic decisions that reduce the environmental risk over annual to decadal timescales. Discussion. The studies described here demonstrate that climate forecasts are already being successfully applied across a number of sectors, including hurricane reinsurance in the marine and agricultural sectors, and for water management, including glacier loss. For example, it's apparent that NTCPs of the frequency and intensity of hurricane activity are providing important information to enable the reinsurance sector to manage risk and to estimate total losses years in advance. It's further observed that relationships in the physical climate system can be utilized to better predict commodity prices and broader macroeconomic indicators, such that forecasts of certain commodity spot prices can be improved with the inclusion of predicted climate variability in econometric models. This is tricky because social scientists will tell you that this information can be used to skew markets and prices by investors and financial companies, whereas governments can use it to make decisions to import earlier or not export, and affect markets as well, even before anything happens. Finally, ocean predictability is relatively high on these timescales and is shown to yield useful predictions of various habitats across a range of economically important fish species in the North Atlantic. While climate model predictions have shown potential to deliver useful information to society, the interpretations of model output to extract the relevant and skillful information is key to realizing this potential. It is the large-scale processes in the climate system that are potentially highly predictable on time scales from months to years, and statistical downscaling of decadal forecasts to regional scales can often be more skillful than the naive use of grid point information. As I mentioned before, model has large grids, and if you pick the closest grid point, you will get all the global coarse resolution problems. But if you have local data and can combine the data with the past forecast, then you can add a lot of value for region specific information at these time scales. That is the statistical downscaling. AI/ML is being used by many to do this. Okay. However, the signal to noise ratio in some regions is anomalously low, such that extremely large ensembles of climate forecasts are often required to capture scale. This is technical again, maybe you already understand. When you say signal to noise, noise in this case is internal variability, just year to year variability like El Nino, North Atlantic oscillation, Pacific Decadal oscillation, and so on. And signal is what is coming out beyond the natural variability, and that's what you want to be able to predict. And there is uncertainty in them, as we said. Mother Nature gives you something, but there are possibilities she could have given. So ensembles and large ensembles are helpful to remove the noise and get the signal out better and increase the signal to noise ratio. Okay. For these and other technical reasons, predicting the near term climate remains a challenge which will necessitate careful development of products which are in great demand now, and many times people don't know that they are there and they can be useful, or that they can be made available if they are in a position to demand. We have presented a small fraction, this is the summary, we have presented a small fraction of the full range of case studies in which NTCPs have been shown to be useful or have the potential to be useful. NTCP will underpin a crucial component of the global framework for climate services, GFCS, which is coordinated by the World Meteorological Organization, and this is the annual to decadal timescales and is key for planning, is a key planning horizon in decision making. However, the utility of NTCPs will only grow where user feedback is actively sought and products are co-developed specifically to fit user demand for information. You know, developing something and putting on the web and hoping that it will be used doesn't work. But if you engage users and meet their requirements from the beginning and understand their requirements and where they come from and what variables they need is also important. As described in Kushner et al., Johannan Kushner, friend from Lamont Doherty Earth Observatory, an enormous effort has been required to deliver operational climate prediction systems. The generation of ensembles of bias-corrected and post-processed predictions is now routinely carried out across multiple centers. This significant community effort is now providing prediction information that can underpin future climate services for end users. With the evolution of operational centers around the globe and continued advances in climate modeling, a more expansive and homogeneous observing network for the oceans, advances from artificial intelligence and machine learning to analyze and extract signal from the noise in combination with user demand for climate services, the capability in near-term climate prediction is expected to grow from its current status, building on these early demonstrations. Lovely, lovely topic, and sorry I have to be brief, but the paper is available. You should definitely go back and read. See you in the next topic, which will be, what will it be? It will be, yeah, it's a nice paper on how desalination can be done from the non-conventional approaches to also help lithium extraction and so on. Okay, see you there.